Deflection in beams, the double integration method. In this lecture, I'm going to illustrate the use of the double integration method for determining deflection in beams. The central equation in this method is deflection V equals to the double integral of m over EI with respect to x. This means if we know the equation for the beam's bending moment, the modulus of elasticity of the beam's material, and the moment of inertia of the cross-section of the beam about the axis of bending, then we can write an algebraic equation for the beam's deflection. This seems to be a rather straightforward double integration operation. All we have to do is to integrate m over EI twice with respect to x, and we have our deflection equation. Well, not quite. What if more than one equation is needed to represent bending moment in the beam? How do we handle the integration of a piecewise continuous moment equation? Or what if the beam is made of several materials? If the modulus of elasticity is not constant, how do we handle two or more e's in this integration problem? And what if the beam has a varying cross-section? Wouldn't that result in varying moments of inertia? How do we integrate m over EI when both m and I are defined in terms of x? In this lecture, we illustrate the application of the double integration method for handling such problems. Before we proceed, let's define another equation associated with this method, the first integral of m over EI with respect to x. This is called the slope equation. It defines the slope of the elastic curve in terms of x. Observe that theta x equals dV dx, since v is defined as the second integral of m over EI. Here, I'm going to use these equations without deriving them. If you want to learn how they came about, see lecture SA12. Obviously, the double integration method involves integrating a function. Hopefully, you still remember how to perform double integration on algebraic functions. If not, please take time reviewing the subject before proceeding with the rest of the lecture. I'm going to cover the double integration method in 4 parts. I start with a straightforward example in order to illustrate the basic steps. In part 1, I'm going to apply this method to a beam having a constant EI and a continuous bending moment equation. In part 2, I'm going to show how to solve problems involving more than one bending moment equation. That is, how to handle beams having piecewise continuous bending moment. In part 3, I will consider a case where the beam is made of aluminum and steel, each having a unique modulus of elasticity. Finally, in part 4, I will show how a beam with a variable moment of inertia can be handled using this method. Part 1. Suppose we have a cantilever beam of length L subjected to a uniformly distributed load having a magnitude of W. We wish to write a deflection equation for the beam. Assume the beam has a constant modulus of elasticity E and moment of inertia I. To use the double integration method, we must be able to write the bending moment equation for the beam algebraically. See lecture SA07 if you are not sure how to formulate such an equation. To come up with the necessary moment equation, I'm going to cut the beam like this. Then, I draw the free body diagram for the left segment. Finally, I sum the moments about the cut point to get my equation. The moment equation is mx equals negative wx squared over 2. Note that this equation is valid for the entire beam. Since Vx equals the double integral of m over EI, I can write the deflection equation as Vx equals the double integral of negative wx squared over 2EI. Okay, W, E, and I are constants. So let's rewrite the equation like this. Integrating x squared once, I get Vx equals negative W over 2EI times the integral of 1/3 x cubed plus C1. Integrating the expression one more time, I get Vx equals negative W over 2EI times 1 over 12x to the power 4 plus C1x plus C2. Note that C1 and C2 are the integration constants to be determined using the boundary conditions. Since there are 2 integration constants, we need 2 boundary conditions. The conditions are deflection at the fixed support is 0, and the slope of the elastic curve at the fixed support is 0. I know that the slope equation equals to the derivative of the deflection equation, so the slope equation can be written as theta x equals negative w over 2ei times 1/3 of x cubed plus c1. Now, let's see how the boundary conditions come into play. Deflection at the fixed support must be 0. That is, L to the power of 4 divided by 12 plus C1L plus C2 equals 0. Slope theta at L equals 0. That is, L cubed over 3 plus C1 equals 0. Solving these equations for C1 and C2, we get. Therefore, the deflection equation for the entire beam can be written as Vx equals negative w over 24ei times x to the power of 4 minus 4l cubed x plus 3l to the power 4. This equation is valid for x between 0 and L. Now, let's use the equation to determine the deflection at the free tip of the beam. Substituting 0 for x, I get V0 equals negative w over 24ei times 0 minus 0 plus 3l to the power 4. So V at the free end of the beam equals negative WL to the power 4 divided by 8 times EI. This was a straightforward application of the double integration method. Now, let's turn our attention to the more challenging cases. Part 2. This example illustrates how to use the double integration method to find a deflection equation for a beam with a piecewise continuous bending moment. If a simply supported beam is subjected to a concentrated load, like this, then bending moment cannot be expressed using a single equation. In this case, we need two equations to correctly represent bending moment. We need one moment equation for the left segment of the beam and another moment equation for the right segment of the beam. Since we have two moment equations, we must write two deflection equations, one for each beam segment. We use this equation to get a deflection equation for the left segment of the beam, and we use this one to get a deflection equation for the right segment of the beam. The general deflection equation is Vx equals the double integral of m over ei. Here is the expanded deflection equation for the left segment. Here is the equation for the right segment. Let's refer to this one as V1 and call this one V2. Also, let's assume EI is a constant for the entire beam. Integrating V1 twice, we get V1x equals 1 over EI times px cubed over 8 plus C1x plus C2. Integrating V2 twice, we get V2x equals 1 over EI times PLX squared over 2 minus PX cubed over 24 plus C3x plus C4, where C1, C2, C3, and C4 are integration constants to be determined using 4 boundary conditions. The boundary conditions are: deflection at the left end of the beam is 0, that is, V1 at 0 equals 0. Deflection at the right end of the beam is 0. That is, V2 at 4L equals 0. Slope of the elastic curve at point B must be continuous. That is, theta 1L equals theta 2L. Deflection at point B must be continuous. That is, V1L equals V2L. Since theta equals dV dx, then theta 1x equals 1 over EI times 3px squared over 8 plus C1. And theta 2 equals 1 over EI times PLX minus PX squared over 8 plus C3. Here are the 4 boundary equations altogether. If we solve them simultaneously for the constants, we get C1 equals negative 7PL squared over 8. C2 equals 0. C3 equals negative 11 PL squared over 8. C4 equals PL cubed over 6. Therefore, the deflection equations can be written as V1 equals 1 over EI times PX cubed over 8 minus 7 over 8 times PL squared X. V2 equals 1 over EI times PLX squared over 2 minus PX cubed over 24 minus 11 PL squared X over 8 plus PL cubed over 6. Let's see how these functions look graphically. The graph of V1 looks like this. The graph of V2 looks like this. Keep in mind that V1 is valid only for the left segment of the beam. The equation should not be used for calculating deflection in the right segment. Similarly, V2 works only for the right segment. So the correct elastic curve for the beam looks like this. This part of the curve is drawn using V1, and this part is drawn using V2. Now, suppose we are asked to determine the location of maximum deflection in the beam. We can do this visually by inspecting the graph of the elastic curve, or we can do it more accurately, algebraically, using equations V1 and V2. More specifically, we know that at the point of maximum deflection, slope of the elastic curve is 0. Here is the slope function for the left segment of the beam. And here is the slope function for the right segment of the beam. Maximum deflection occurs either in the left segment or in the right segment. If it occurs in the left segment, then the point of maximum deflection must be located between 0 and L. To decide if this is true, we set θ1 equal to 0, then solve for x. If we get a value between 0 and L, then we have indeed located the point of maximum deflection in the left segment. Otherwise, maximum deflection occurs in the right segment. So, setting θ1 equal to 0, we get x approximately equals to 1.53 L. Since this point is not between 0 and L, then maximum deflection does not occur in the left segment. Therefore, it must occur in the right segment. Let's see if this is true. At what x value is θ2 0? Solving this equation for x, we get x equals 1.75 L. Since this value is between L and 4L, then we conclude that maximum deflection in the beam occurs in the right segment of the beam, at x equals 1.75 L. Now, we can determine the value of maximum deflection by evaluating V2 at this point. Part 3. This example illustrates how to use the double integration method to find a deflection equation for a beam consisting of multiple segments, each having a unique modulus of elasticity. We wish to formulate a deflection equation for a beam made up of two segments, an aluminum segment and a steel one. It is important to note that here we cannot assume a constant modulus of elasticity for the beam, as aluminum and steel have different E's. Let's refer to the modulus of elasticity for aluminum as E sub A, and use E sub S for the modulus of elasticity of steel. For ease of calculations, let's assume the ratio of E sub S to E sub A is 3, or E sub S equals 3 times E sub A. Both segments have the same cross-section, therefore moment of inertia I remains constant for the entire beam. Since the beam is subjected to a concentrated load of P at point A, we can write the bending moment equation as mx equals negative px. Similar to the previous example, here we need to set up two deflection equations, one for the aluminum segment and one for the steel segment. The deflection equation for the aluminum segment is given by the double integral of m over E sub A times I. Let's refer to this equation as V1. V1 is valid for x between 0 and L. The deflection equation for the steel segment is given by the double integral of m over E sub S times I. We refer to this equation as V2, which is valid for x between L and 2L. Substituting negative px for m, we get Furthermore, since E sub s equals 3 times E sub a, let's rewrite V2 using E sub a. Here is what we have so far. This is V1, and this is V2. Now integrate each function twice to get the deflection equations. Then V1 becomes negative px cubed over 6 e sub ai plus c1x plus c2. And V2 becomes negative px cubed over 18 e sub ai plus c3x plus c4. To solve for the integration constants, C1 through C4, we need 4 boundary condition equations. We can get 2 equations by imposing 2 continuity constraints at point B, where the aluminum segment is attached to the steel segment. Equation 1. Deflection must be continuous at B, that is, V1 at L equals V2 at L. Equation 2. Slope of the elastic curve must be continuous at B, hence θ1 at L equals θ2 at L. The remaining 2 equations come from the support conditions at the fixed end of the beam. At point C, deflection and the slope of the elastic curve must be 0. That is, V2 at x equals 2L must be 0, and θ2 at 2L must be 0. The slope equation can be obtained by taking the derivative of the deflection equation with respect to x. So, θ1 equals negative px squared over 2e sub ai plus c1, and θ2 equals negative px squared over 6e sub ai plus c3. Here are the 4 equations. Solving these equations for C1 through C4, we get Making proper substitutions in the deflection equations, we get V1 equals negative p over 18 e sub ai times 3x cubed minus 18xl squared plus 20l cubed. And V2 equals negative p over 18 e sub ai times x minus 2l squared times x plus 4l. The deflection of the beam is given by V1 when x is between 0 and L, and by V2 when x is between L and 2L. These functions, when plotted between 0 and 2L, look like this. Here is V1, and here is V2. To define the beam's elastic curve, we use this part of V1 and this part of V2. To summarize, assuming you already know how to formulate moment equations algebraically and how to integrate continuous functions, then the double integration method lends itself to 1. Determining the number of equations needed to correctly model the beam's deflection, and 2. To identify and use the necessary boundary conditions for determining the integration constants. Let's see if you can correctly determine the needed number of equations and the necessary boundary conditions for these beams. Pause the video if you wish to work on these problems, as the answers will be displayed shortly. Solution for problem 1. We need 4 deflection equations for this beam. Since each equation has 2 integration constants, we need a total of 8 boundary equations. They are: deflection at the roller support must be 0. Deflection at B, where the steel and aluminum segments meet, must be continuous. Slope at B must also be continuous. Deflection at C, where the aluminum and steel segments meet, must be continuous. Slope at C must also be continuous. Deflection at D, where the concentrated load is applied, must be continuous. Slope at D must also be continuous. Deflection at the pin support must be 0. Solution for problem 2. We need 3 deflection equations for this beam. Since each equation has 2 integration constants, we need a total of 6 boundary equations. Deflection at the pin support must be 0. Deflection at B, where the beam rests on an internal roller, must be continuous and 0. This means both V1 and V2, evaluated at point B, must yield 0. Slope at B must also be continuous. Deflection at C, where the aluminum and steel segments meet, must be continuous. Slope at C must also be continuous. Solution for problem 3. We need 3 deflection equations for this beam because the distributed load divides the beam into 3 segments. Since each equation has 2 integration constants, we need a total of 6 boundary equations. Deflection at the pin support must be 0. Deflection at B must be continuous. Slope at B must also be continuous. Deflection at C must be continuous. Slope at C must also be continuous. Deflection at the roller support must be 0. Solution for problem 4. We need 2 deflection equations for this beam. Since each equation has 2 integration constants, we need a total of 4 boundary equations. They are: deflection at the pin support must be 0. Deflection at B, where the beam rests on an internal roller, must be continuous and 0. This means both V1 and V2, evaluated at point B, must yield 0. Slope at B must also be continuous. Part 4. This example illustrates how to use the double integration method to find a deflection equation for a tapered beam. Consider a cantilever beam with a rectangular cross-section that changes size. The height of the rectangle changes linearly from h at the free end to 2h at the fixed end. We want to write the deflection equation for the beam. We know the general equation for deflection, but here moment of inertia I cannot be treated as a constant as it varies with x. So we need to write I as a function of x before we can integrate m over ei. Let's start by defining a height function. I call it h bar. H bar x equals h times 1 plus x over 10. This is a linear function which should give us h when x is 0 and 2h when x is 10. Let's see if the function indeed generates the correct values. So if we substitute 0 for x, we should get h. Check. If we substitute 10 for x, we should get 2h. Check. For a rectangular section, moment of inertia about the axis of bending is 1 over 12 bh cubed. So for this beam, we get I equals 1 over 12 bh cubed times 1 plus x over 10 cubed. Let's refer to 1 over 12 bh cubed as I naught. Then I can write Ix equals I naught times 1 plus x over 10 cubed. So what is I naught? It is the moment of inertia of the section at the left end of the beam. The general displacement equation can now be written like this. Let's assume a constant E. Then Vx equals 1 over E I naught times the double integral of m over 1 plus x over 10 cubed. Given that we have a downward concentrated load of 1 kilonewton applied at the free end of the beam, the bending moment equation can be written as mx equals negative x. Therefore, the deflection equation becomes, if we integrate the function twice, we get Vx equals 1 over E I naught times 5,000 over 10 plus x plus 1,000 times natural log of x plus 10 plus c1x plus c2. To determine the integration constants c1 and c2, we need two boundary conditions. We know that slope and deflection at the fixed support are 0, so we can write theta at 10 equals 0 and v at 10 equals 0. Theta can be obtained by differentiating v with respect to x. That is, so we can write the boundary conditions as solving these equations for C1 and C2, we get C1 equals negative 75 over 2, and C2 equals negative 2,871. Therefore, the deflection equation can be written as Vx equals 1 over E I naught times 5,000 over 10 plus x plus 1,000 times natural log of x plus 10 minus 75 over 2 times x minus 2,871. We can now use this equation to calculate deflection in the beam. For example, maximum deflection, which occurs at the free end, can be determined by substituting 0 for x in the deflection equation.